Okay, chapter 6, new life, work and energy, totally different approach for problem solving, analysis, and good news if you can't solve problems with kinematics and dynamics approach, then chapter 6 might give you a chance to actually solve problems in a totally different way. Once you understand how to calculate work done by different forces and how to apply conservation of energy principle, you can solve problems without any second Newton's law equations or kinematics equations. You'll be just calculating work and energy, and that is enough to solve for many different things right away. So for constant forces, you definitely want to use the second Newton's law and the third Newton's law for action-reaction questions. But what are we going to do if forces change over time? Well, the short answer is we can do calculus, right? If the force is a function of time, then you can do also many things to calculate those changes and still apply dynamics laws and kinematics. But that requires calculus, right? And it's a different story. So instead of going through calculus, you can actually try to analyze what we call energy of a system. And there is a conservation of energy principle that is general, like one of the fundamental principles for physics. So mastering the idea of energy can help you to solve problems without even bothering all those intermediate steps. So definitely a valuable parameter to understand and to be able to work with. A good news, modern physics is pretty much solved with energy and work. So for all of those fancy connections between energy and matter, well, you need to understand work and energy principles. And you definitely can use energy for electricity and magnetism as well. I'm pretty sure you've heard about voltage, which is your electric potential energy with respect to a charge. So see how it's still connected to energy. The principle of energy is a fundamental one and definitely worth understanding. Okay, let's start with the idea of the work, how you calculate work done. And you see how the given is that force is constant. Force doesn't change. And two cases to think of. First case, you speed up on a freeway. Why is that so? Well, because there is some kind of a force, and that force propels your car, and you gain acceleration from that force. And the second case, you make a stop in front of a traffic light. Well, clearly there is friction. It's the friction force that has stopped your car. And what you have to think of is the work done by a force on an object, on a system. So remember how it was just position, velocity, and acceleration. And we didn't discuss any reasons for acceleration. And then we said, okay, we have a force, which is the reason to gain acceleration. And now the next step in this logic is those forces, they can do work. Okay? So there's kinematics, then there's dynamics. And then on top of dynamics, you can say, okay, there is a force that causes acceleration, and that force can actually do some work. And work turns out to be an energy transfer to or from the system, depending if it's a plus or a minus value. So this is the last step in the logic. Once you can perform operations on that logic, you can solve a lot of physics problems just by doing the conservation principle of energy or calculating the work done, and then change in kinetic energy is the work done. Yeah, do not confuse the word work with what you used to. Say, you do your homework, and you say, my head hurts because I'm doing my homework. Well, there is work in the homework, but your mental work has nothing to do with what we call work in physics. Okay, work is a special definition, and no matter if it's algebra based or calculus based, there is either a force and displacement, and you have to think about a dot product between the two. So it's a totally different definition from what you used to. Okay, uh, like you think, oh, I'm doing so much work, but if you're just sitting in your chair and just doing your mental work, this has nothing to do with work in physics. So in order to do work on an object in terms of physics, you have to think about energy transfer, okay, to the system or from the system. Okay, so here's an example. You throw a baseball, and that means you do work on the ball by throwing it, giving it some kinetic energy of motion. And let's say you try to push a wall, and the wall just keeps on standing still. Then there is no displacement. There's no displacement for the wall. There is no work done on the wall. So even though you are like sweating and you're tired from pushing that wall or say heavy desk, and if the desk never moves, no displacement, no work was done on the desk or the wall. So work, it's the energy transferred to or from an object or a system by means of a force acting on it. Good news, it's not a vector. It's just positive or negative value, right? And no particular direction for work done. But work is a dot product between other two vectors. So you still have to think vectors while calculating work. And you want to multiply the force, which is one vector, by the displacement, which is another vector. And it's going to be a dot product. And for that, you have to think about a cosine of angle between the two vectors. So even though the final result is a scalar, that's what we call scalar product, dot product, you still have to deal with vectors in the first place. So make sure you understand that force can be one direction, displacement can be the other direction, and then the angle between the two can be, everything. And you have to consider three things for calculating work in the first place. And drawing a good sketch is still a very good idea. It will help you to see what kind of angle we're talking about between those two vectors. So here's an example of pulling a crate. So lady's trying to pull the crate, and the force is clearly a tension in the cord. And see, this is the angle I'm talking about, angle theta, because you have the force along the cord. That's your definition for tension force. And then you have displacement. The crate moves horizontally. That's the initial, that's the final position. Displacement is final takeaway initial. So you see the blue vector D. And the work by that was done by this force is the force by itself, the magnitude of it, times the displacement, and times the cosine of angle between the two vectors, the force and the displacement. So this is the angle of reference, angle theta. So F times the D times the cosine theta is your general way of calculating work done. If force is not constant, then it's going to be calculus approach, and you would still do the same, but you would split the force into many different pieces and still do the D dot F. Dot means the dot product. So vector times a vector times the cosine of angle. Fun fact, it's not a vector anymore, it's just a scalar. And be careful, it can be positive or negative. Is it the work that you do on the system, or is it the system that does work on the environment, right? That's where the difference is. Say, for some reason, the answer is $5. But is it me giving you $5 or you give me $5? The answer is still $5, but there is a difference. Me giving you or you giving me $5, right? So work being positive or negative, it's a very important concept. You can't ignore, let's say, a negative work for some reason. Negative means that there's energy transfer out of the system, not to the system. Okay, another option. You carry a bag of groceries and gravity pulls downward on the bag and you support the bag with your hands, the force of push against the gravity, and you carry it horizontally, so displacement is perpendicular to both forces. Check this out. It is the displacement times the force and the cosine of angle. What kind of angle are we talking about here? Its force is upward, displacement is horizontal. What's the angle between? 90 degrees. Cosine of 90 degrees, everybody knows it, it's 0. So yeah, force is there, displacement is there, but because the angle is 90 degrees, you have a work done 0 because it's cosine of 90 degrees. Same thing for gravity. Check it out. Gravity goes downward. Displacement is perpendicular. What's the angle between those two vectors? 90 degrees again. So what's the work done by gravity? Onto this displacement, that work is 0. Cosine of 90 degrees is 0. So no work is done here because lifting or lowering the bag, that will create a 90 degrees angle between the two vectors. So work done, it's very tricky. It's totally different from what you're used to. So focus on definition. You have displacement vector, you have force vector, and then there is a cosine of angle between the two vectors, displacement and the force. Units. Units are, for force is newtons, for displacement is meters. So you have Newton meters. And please do not leave it like that, because later on we'll discuss torques, and torques are good for rotational motion, and unit-wise, it's also going to be Newton meters for a torque. So in order to get around the confusion, like is it a torque, or is it a work done, or the energy, you have to think joules. Joules are Newton times meters, and if you want to talk about work or energy, then it's got to be joules. Do not stop at Newton meters. You have to show me joules. And for torques, you will show Newton meters. So Newton meters please don't show me that as a final answer for energy or the work problems. For energy and work, it must be joules. So drawing a free body diagram with forces and vectors is still paramount. It's still very important. Showing X and Y coordinate system, still important. And Newton's laws might show you some unknown forces. You can calculate forces. And then if it's the work done by a force, what do you say? It's force, displacement, and the angle between the two vectors. So we're still working with dynamics. You might actually start as far as kinematics. If kinematics is given and you figure out acceleration, then you can figure out the force, and then you want the work done by that force. That would be the strategy to solve such a problem. So we're still working with what we had before, and on top of it, now we have to calculate work done. Or maybe backwards. You start with work done, and from there you can figure out the forces, and then acceleration, and then all the kinematics parameters. Yeah, chances are it's going to be more than one force. So instead of just one work, from one force, you'll get multiple forces and multiple works. And then you combine all those pieces together and you get the net work. Remember, we had net force. So for a net force, you would get net work. Net means like the sum of all the works from all the forces. It's really up to you if you want to find all works and sum the individual terms, or get the net right away and then work from there. It really depends on the problem. Some problems would ask you for what is the work done by gravity? What is the work done by friction? What is the work done by tension? Or there will be a problem would say, find the net work. And that means you have to find all the works combined. Doesn't really matter. You still have to be able to do both scenarios and calculate work done by all the forces anyways. Yeah, if force is not constant, do not panic. There is calculus, and you divide the distance into small pieces, calculate the Riemann sums, and that is replaced with antiderivatives, integration, and you add them up. At the end of the day, your general understanding of work would be the area below the curve. See, there's the curve, the function for force versus the distance traveled. So force is your function, distance d is your variable, and whatever is the function, the area below is what we call work. Antiderivative of force dot displacement, that's the calculus definition. You will do that later at the calculus level. For now, you will not see any force that is not constant other than the spring force. And for that, you'll just do the average between the initial and the final. We'll discuss that a little later. Okay, so for that work, we have to connect that to energy transfer. So what is energy? Energy is just a number. Yeah, some textbooks would define energy as the amount of work that can be done by the system, but this is a violation of thermodynamics definition for work. And yeah, you can think about work done by a system, but it's not 100% truth definition. You want to reconsider that in thermodynamics. That's why you can't really say it in general. So in general, for energy, just say a certain number, scalar, that you assign to an object or a system of objects. And energy cannot be created out of nowhere, and you cannot lose energy. That system cannot lose energy for no reason. And there are different types of energy: kinetic, potential, electric, chemical energy, nuclear interactions. It's also many variations for energy. And you can transform energy from one type to another. But once again, you cannot lose energy for no reason, and you cannot create energy out of nowhere. So it is conserved in a closed system. Closed system means no energy enters the system or leaves the system. And if no energy leaves or enters the system, the total amount of energy of different types must be conserved. And you need energy to proceed with motion. If there is no energy in the system, then energy can't move anywhere. So those are the foundations. Let's discuss them in details. The very first type of energy is called kinetic energy. And there is a capital K. You can say capital K or KE or E sub K, doesn't really matter. But for many different textbooks, you'll find different notations. But the most common notation would be just capital K. And it's a straightforward connection. The faster an object goes, the faster it moves, the greater the kinetic energy. So with this approach, you should understand that you have only two options. Kinetic energy can be zero when you don't move anywhere, just sitting still, or it's a positive number because you go in a certain direction. See, it's not a vector, and it would be just a certain amount of kinetic energy stored in the system because the system is moving in a certain direction. So kinetic energy cannot be negative. It's either zero or a positive value. So how do you calculate kinetic energy? Say I say capital K or KE or E sub K, doesn't matter. Choose the notation that you like the most. And the way you calculate it is 1/2 mass times velocity squared. See how velocity goes squared. So even if you had a negative value for velocity because you're going in the opposite direction, then you square the negative, and that becomes positive. And mass is also a positive value. So 1/2 times a positive times a positive. See how kinetic energy cannot be negative. It's only a zero if velocity is zero, or it's some kind of a positive number if you go in a certain direction with certain speed. Unit-wise, once again, joules. We got kilograms for mass. We got velocity squared, which is meters squared per second squared. And if you look closely for the work done, it was joules as newtons times meters. And in here, you also have newtons as mass times acceleration, kilograms times meters per second, times meters for the displacement. So meters and meters give you meters squared, and you're left with joules. So either newtons times meters, that's joules, or thinking through the fundamental, the base units, you see how kilograms multiplied by meters squared and divided by seconds squared also give you the unit of joule. For energy, do not say Newton meters. Newton meters are reserved for torques. Make sure you show me joules for units. Yeah, don't forget that for our classical mechanics, we are limited with the speed of light. And once you travel close to the speed of light, this formula will need a relativity coefficients. So it's only 1/2 mv squared up until you start getting closer to the speed of light. And at that level, you will have an extra coefficient to this formula. We will not solve anything with the speed of light in this course, so you don't have to worry about relativity, but later on, you will see a change to this formula once general theory of relativity will apply. So a normal car, remember, everything is a particle with a certain mass. This is your, about 3,000 pounds, so 1,500 kilograms going in a certain direction with 10 meters per second will have exactly the same kinetic energy as going in the opposite direction or in other direction at the same rate, because it's 1/2 the mass, and whatever is the magnitude for velocity goes squared, and that's it. See how direction doesn't matter. For energy, you're only concerned as magnitudes, the scalars, not the direction, which makes problem solving much easier, and you don't have to worry about many different vectors. The moral of the story is you have to be careful with your speed because it goes squared. You double your speed and your kinetic energy quadruples because you square the double as well. And let's say it was 10 meters per second, and that is enough to destroy a medium tree on your way. And doubling the speed makes it 4 times for the kinetic energy, which means you will destroy 4 trees. And if it's 3 times the original speed, then you square the 3, and that becomes 9, and you can destroy 9 trees on your way. So traveling just a speed limit on the highway is pretty dangerous because your car has enough energy to destroy an alley of trees, like nine medium trees. You should be careful. You cannot go over the limit because the faster you go, the faster your kinetic energy changes. And remember that even though it's 1/2, but don't forget that the velocity goes squared. So everything that you have is a change in velocity. You're in charge of a huge amount of energy while driving a car, and a lot of damage can be done to the environment, and that's why people die in car accidents. Even 67 miles per hour is enough to do a lot of damage to not only your car, but other people's cars and people's life. So be careful. On to a little analysis for why the work is the force is multiplied by displacement. Let's go with simple case when the force is constant. And with constant force, you expect constant acceleration. So kinematics equation applies. And if you solve the third kinematics equation for acceleration and plug it back into the second Newton's law, you will get this expression, and what you see on the left is just the 1/2 mv squared. It's 1/2 mv squared at a certain moment of time minus 1/2 mv squared as initial condition. So this is the change in kinetic energy, and change in energy is the work done. So your work is force times displacement, and not just a force, but the force onto a certain x-axis. And it's not just x-axis, can be y-axis, can be z-axis. So that's why you have only the component that is adjacent to a certain displacement vector, and that's why you have a cosine of angle on the right as well. So work is force dot displacement, or you say force by itself, displacement by itself, and the cosine of angle between the two vectors. And you can see how work is also a change in kinetic energy. This principle is what we're going to use all the time to solve all sorts of problems. So work and kinetic energy are equated. They must have the same units, which is true. Both units are joules. You got joules for work, and change in kinetic energy would be joules minus joules, still joules. And one more application for definition for work right away, so that you keep in mind a very important principle about centripetal forces. Remember, we did last chapter, we discussed circular motion. We said that there is centripetal acceleration, and centripetal acceleration is caused by centripetal force, and there is a linear velocity vector that is tangent to the trajectory, and that centripetal force can be either gravity or friction or tension forces. So let's try to figure out how much work will this centripetal force produce. See how velocity vector is tangent, and therefore displacement is also tangent. And the force is towards the Earth. For the moon, you got the force and displacement at 90 degrees angle. And if it's 90 degrees, then work done is force, displacement, and the cosine of 90 degrees, which makes it 0 once again. You have 0 work for this force of gravity for the moon versus the Earth. And if you'll take a look at the tension force being centripetal, you'll find the same result. Centripetal forces produce 0 work because they are always at 90 degrees with respect to displacement. So centripetal forces do no work because they are perpendicular to the direction of motion. Now, be careful with action-reaction pair of forces. Read the question, because sometimes the question is how much work is done by the hammer on the nail. And hammer on the nail, the force is to the right. In this diagram, nail is hit by the hammer, and the force is on the nail is to the right. Or the question can be about the reaction force, because for any action there is equal and opposite reaction, and nail will hit the hammer with exactly the same force in the opposite direction. So what would be the work done? Well, displacement is still to the right, and force from the hammer on the nail would be force, displacement, and what's the angle between those two? 0 degrees. Cosine of 0 is 1, positive 1. But if it's the question about the nail on the hammer and the force is opposite, Then force is to the left, displacement is still to the right, and the angle between the two vectors is 180 degrees. And cosine of 180 degrees is -1. So the work would be negative. Even though the value would be the same, but work done on the nail is positive and work done on hammer is negative. This is what I will be grading the most. That's the most important piece for grading. If you say 5, but the answer is -5, you can't say, oh, it's just 5 anyways, and I got it right. No. If the answer is 5 and you got -5 or vice versa, then it's a horrible mistake. You just made a very, very bad mistake. Keep track of whether the value is positive or negative. It's like, once again, I give you $5 or you give me $5. It's still $5, but there is a difference. Okay, so I've already mentioned that after you do the kinematics and dynamics, so this is kinematics, this is dynamics, and you play with those expressions, you will end up with this particular expression. And it's just a definition for kinetic energy. We defined kinetic energy as 1/2 mv squared. So final value for kinetic energy, take away initial value for kinetic energy, is the work done by a force over this displacement with respect to a certain axis. This is the work kinetic energy theorem or work kinetic energy principle, whatever you call it. This is your best friend to solve pretty much all the problems outside of dynamics and kinematics approaches. Every time you see that there's just not enough information for kinematics and dynamics, give it a try with change in kinetic energy work done theorem, and you might get lucky and get to the solution really fast. Okay, particle moves along an x-axis. Kinetic energy of the particle increases, decreases, or remains the same. Well, if it's from -3 to -2, it looks like it is increasing because -2 is greater than -3. But you got to remember that we don't care about negatives. For kinetic energy, it's just 1/2 mv squared. And once you square the negatives, they become positives. And -2 squared, that gives you 4. And -3 squared gives you 9. So it's 4 subtract 9. And the answer is negative. So the change is negative. That means energy is actually decreasing. So even though the -2 is greater than -3 in terms of absolute value, you still get a decrease in overall value. Now it is a change from -2 to +2. And once again, +2 should be greater than -2, so you should expect an increase. But once again, we don't care about negatives, and it's -2 squared and 2 squared. This is 4 minus another 4. 4 minus 4 is 0. So you essentially get no change. No change means energy remains the same. So Be careful while calculating kinetic energy, especially if there's some kind of a negative involved. Do not make any fast decisions until you do the actual calculations and see for yourself if the change is positive, negative, or zero. A lot of options are on the table. And because you square everything, your negative really doesn't matter. It's the magnitude that matters, not the direction. In each case, is the work done on the particle positive, negative, or zero? Work is negative. Why is that so? Because change in kinetic energy is negative. Easy as that. Remember the principle, the original theorem? Change in kinetic energy is work done. If change in kinetic energy is negative, then work done is negative. If change in kinetic energy is positive, then work is positive. If change in kinetic energy is zero, work done is zero. So energy decreases, work is negative. System loses energy. Energy remains the same, work done is zero. There is no energy transfer to or from the system. Okay, done with kinetic energy, on to the potential energy. Potential energy is a tricky one because it really is a replacement for kinetic energy when you're just sitting still. If you are sitting still, your kinetic energy is zero, right? But let's say you're sitting still at the top of a hill, and then you just let go and just say drop a ball, and the ball starts accelerating downward because of gravity. So that ball, or your body, if you want to do the bungee jump or whatever, has what we call potential energy. It's the configuration of a system of many objects which exert forces on one another. Say, the ball in your hand, and you let it go. So you're going to think about the earth pulling on the ball, and the ball pulls on earth. And then you're going to talk about elastic potential energy. That would be an object on the spring. So spring would be the medium to for that kind of interaction. So for potential energy, for now, just think about gravitational potential energy and elastic potential energy, and that's it. For this course, only when you see force of gravity or the spring force, then you can think about potential energy. Later on, with electricity and magnetism, you'll be introduced to electric potential energy, and that would be a different story. For now, just two types of potential energies for you to remember: gravitational potential energy and elastic. Spring force or gravity, those are the only conservative forces that you can associate potential energy with. I'll be more specific on conservative forces later. So Earth and the bungee jumper, there is gravitational potential energy. Yeah, for potential energy, you can say capital U as notation, or PE, or E sub P. It's up to you how you want to do the notation. The most common notation will be capital U. Capital K for kinetic, capital U for potential, and gravitational potential energy is there because of the force of gravity. And another system is the jumper and the bungee cord. You know how bungee cord can stretch for, quite a distance, and the actual amount of stretching times the spring force would give you the elastic potential energy stored in that system. We'll solve a few problems on that, and you'll see how this works. So either gravitational potential energy or elastic potential energy are the two potential energies for this class. How much of a potential energy do we have? How do you calculate it? Well, let's think about gravity. And there's an object that you push upward, and there is an external force from the hand on the object. So you raise it to a certain height, say from the initial coordinate y sub 1 to the final coordinate y sub 2. There is that change in vertical position. So your displacement is upward from initial to final. This blue vector D shows the displacement. And there was a force from the hand on the object. So now the object is here. Now, once you raise it, you let it go. What's going to happen to that object? The object will free fall towards the earth. Why is that so? Because there is a force of gravity, the mg, that we discussed in previous chapters. And the work done by gravity in this case will be negative because displacement was upward and the gravity is downward. So the moment you raise the object up, gravity does the negative work. And once you let it go, displacement is downward, force of gravity is downward, and it's the positive work done by gravity. So be careful with your orientation of vectors, displacement versus the force. What kind of a force we're talking about? Work done by the external force by hand during your pushing upward is force, displacement, and the cosine of 0. Force is up, displacement is up. So the angle between those two vectors is 0. Cosine of 0 is positive 1. And D is H. You can see how H is the notation. And it's mgh for you to calculate that work done by hand onto the object. And because H is the difference between the two vertical positions, you can just simplify it to y, not y sub 2 minus y sub 1, but just y for a certain position with respect to a 0 level, which is usually the ground. Ground is the 0 level. Your y sub 2 will represent the y in this equation. Yeah, so if you let go of that object, then your gravitational potential energy will be transformed into energy of motion, kinetic energy, right? You hold this object and then you let it go. So all that gravitational potential energy starts converting into energy of motion. The object will start falling. That means increase in motion, increase in kinetic energy. So where do we measure y from? It's really doesn't matter. It's your choice of your 0 level. But once you choose your 0 level for position, you have to be careful and always refer to that 0 level. My recommendation for you is to just choose surface of Earth as 0. So everything on top of that level would be positive. And if it's somehow below that 0 level, then it's going to be a negative. So your 0 level at Earth really makes the most sense in terms of altitude being, positive, and you get positive value for gravitational potential energy. And below the surface of the Earth, which you probably will not have to work with, that would be a negative. So only the changes in gravitational potential energy are important. And the change is final takeaway initial. So if your initial is 0, then it's just the final that you really have to calculate and worry about. So surface of Earth is your 0 level for gravitational potential energy, and that will eliminate the most amount of negatives in your solution. For elastic potential energy, think about a spring, and you have a ball in your hand, and you compress the spring with that ball, and you let it go. What do we have? We have a motion of the ball. Ball accelerates in the opposite direction because the spring stretches back to its normal unstretched position. So it is the elastic potential energy that is converted into kinetic energy once again. You had no motion here. It was all elastic potential. Now you let it go, and elastic potential is converted into kinetic energy. And good news, the total amount of energy stays constant, so you can always do the balance. It was before the interaction a certain amount, and after you let it go, it will be exactly the same amount for the system in terms of energy. Yeah, the energy is going to be of different type, but the overall value for energy will not change. It will stay conserved. How much of a spring force do we have? That is dictated by what we call the Hooke's law. And the spring force, it's the negative K times X. K is the stiffness of the spring, or you can think about coefficient of a spring. This is just the stiffness of a spring that just it's a parameter of a spring itself. The more force is produced, the more the stiffness, and the K by itself stays constant for a certain spring. That's just a coefficient, just a parameter of a spring itself. It's either given, or you can figure it out right away and then use for your conservation principle solutions. I want to point out that there is a negative. Why is it a negative? Why is there a negative? Because there is an external force that you want to say stretch out the spring, and see how the spring force is in opposite direction. It is trying to move the spring back to its unstretched position. Or if you compress the spring, then the spring force is once again opposite to the external force because it is trying to bring the compressed spring back to unstretched and uncompressed position. So spring force is always opposite to the external force. And sometimes the question is, how much of a spring force do we have, or how much of an external force do we have to apply? And the difference is, one is a positive, the other one is a negative. Make sure you answer the question correctly on which force are we talking about. And X is just the amount of stretching. See, the X can be in one direction or the other direction. Units must be meters. Force must be in newtons. By the way, the stiffness will end up being newtons per meters in the dimensional analysis. And X can be positive or negative. So be careful with the sign here as well. So yeah, K is the spring constant or the stiffness. And minus shows that the spring force always opposes the displacement. Delta X, or X, is your displacement, and negative shows the direction for the force, being opposite to displacement. This spring force is one of those forces that do not stay constant. Remember, we started our calculations with forces being constant, and that produces constant acceleration. For the spring force, that's not true. For the spring force, if it's K times X, the more you stretch or compress it, the more the spring force you have present. And at the calculus level class, we would just do the antiderivative, and that would be it. We don't know antiderivatives yet for this class, and we have to do the average value to simplify our calculations to be able to do calculations. So your elastic potential energy, which you can say capital U or PE elastic or E sub elastic, it's just the average between the 0, which is the minimum value, and a certain value of x, and kx gives you kx squared. The average between 0 and kx squared is 1/2 times kx squared. Say kx squared is 20, and the minimum is 0. What's the average? The average would be 10, because it's 0 versus the 20. The range is 20, cut it in half, and you get 10. So average value, that's your best bet for calculating elastic potential energy for now. Once you hit the calculus-based class, you will get the same answer, but using antiderivatives and the formal definition for elastic potential energy. So 1/2 kx squared versus mgh, mgy. Those are the two formulas for you to keep in mind while calculating potential energy of a system. Gravitational potential energy, mgy, mgh, and elastic potential, you say 1/2 kx squared, k being the stiffness, x being the displacement. Be careful with units, system international units only. That's what we have. Now, two types of forces, conservative and non-conservative. For conservative forces, it doesn't matter how you get from initial to the final position. The work done will be the same. And for force of gravity or the spring force, it turns out that if you get from point A to point B as trajectory 1 or trajectory 2, the value for work done is going to be the same. And if you're going to go from A to B and then B to A, the overall round trip gives a total work of 0. Same applies to spring force and electric force. For your next semester, electric force will also produce the same result, and that's how we call them conservative. So gravitational force is conservative, and instead of solving a problem when you go down and up and down and up, you can just say, we're going to go this way and then that way, and in order to calculate the work done, this is a much better approximation. This is much better, it's a simplification of calculating the work, and the result is the same. So for gravity or spring force, you definitely want to go with this way rather than going through curves and a lot more calculations. So simpler path instead of a complex one produces easy solution, and that's the reasoning for defining potential energy as well. You can only define potential energy for conservative forces. You cannot do that for non-conservative. Non-conservative, by the way, is when it's a false statement for the same amount of work from initial to final, no matter what. Say for friction force, the more the distance traveled, the more energy you're going to lose from mechanical energy to thermal energy, because every time there is friction, there is a heating up of surfaces, and you lose some of that energy to thermal energy. And the more the distance, the more the losses are, and you will not get the same result for work done. So potential energy can only be defined for conservative forces, and conservative forces, once again, for this class is only gravity and spring force. Other forces, you can't say conservative, you do not define potential energy. Friction is not conservative. Thermal energy is not a potential energy. Easy as that. We have a figure with 3 paths connecting points A and B. Single force does the work. Is force conservative? Well, A to B, positive 60. B to A, also positive 60. And A to B, negative 60. Definitely a no answer, because A to B is positive 60 and A to B negative 60 is not possible. For a conservative force, you go A to B here, you go A to B there. It cannot be negative 60. It has to be positive 60 if you want the conservative force. For definition, no matter how you get from A to B, it's always going to be the same number, and it's not the same here. It's 60 or negative 60 for the same trajectory, for the same displacement. You can't say it's conservative. How would you make it conservative? Well, A to B is 60. B to A would be negative 60. And this A to B, positive 60. This way, it would be conservative. The sum total between kinetic and potential energy is called mechanical energy. So K plus U is what we call mechanical energy, E sub mechanic. And good news, for all the cases when you don't have friction, or it says frictionless, or you can neglect friction, you say mechanical energy of a system is conserved, because your kinetic and potential total cannot be changed to other forms. And it's K plus U equals K plus U, K plus U before something equals K plus U after something. And you solve for what's missing using what's given. Very easy and straightforward calculations. Change change in kinetic is the negative of the change in potential. Or you say just K plus U equals K plus U. Those are the same statements. And mechanical energy is conserved unless you have friction, and that friction will transform some of that mechanical energy into thermal energy. So every time you see a problem and there's not enough kinematics or dynamics, and it says no friction, you really want to use this approach to solve it. K plus U equals K plus U. I'm pretty sure that would be enough to solve for what's missing. Or at least you will get some new data, say initial or the final velocity, and then you can use it to solve kinematics. Or maybe you get the mass that was missing, and then you can solve dynamics, because you will not know masses. So if only conservative forces are present, no friction, then kinetic energy, potential energy can change, but the sum cannot. And you say change in kinetic plus change in potential is 0. So overall change is 0. And this is your easy case for problem solving. The easy case means no friction. Yeah, I suggest you always choose the lowest point in the system as 0 level. Usually it's the ground level, the surface of the planet. So the highest point would be the maximum potential, minimum kinetic, and once again, K plus U stays constant. There's no change to that value. Be careful. Common error here is you say K plus U equals to 0. No, K plus U is not 0. It's the change in kinetic and the change in potential that add up to 0. It's the 0 change in value, not the value by itself. The value by itself can be any number. That really depends on the system. But the overall change in terms of energy is a 0 change if there is no friction. Okay, let's see how problems are solved. There is a gentleman holding a rock, and while you hold it, it's all potential, gravitational potential to be more specific. The rock is sitting still, so no motion, no kinetic energy. And then you let it go, the rock will accelerate and hit the ground. And once it hits the ground, if ground is your 0 gravitational potential energy level, then potential energy is just 0. And it's going to be all kinetic. So all of your potential energy has been transformed into kinetic energy. And good news, K plus U equals K plus U. So 1/2 mv squared plus mgy for the topmost point would be 1/2 mv squared plus mgy for the bottom point. And you see those energy diagrams. It was all potential, now half potential, half kinetic, and eventually it's all kinetic, no potential. And what do you say for the total energy? Total mechanical energy stays constant. And no friction. Yeah, you have to neglect air resistance for saying K plus U equals K plus U. A roller coaster problem, there are two types, with friction and with no friction. If there's no friction, what do you say? The roller coaster had potential energy, and then it has accelerated, and there's a speeding up, so it's more of a kinetic energy at the bottom, less potential, and then it is trying to get back to a certain altitude, and there's again potential and less kinetic. But the sum, kinetic plus potential, stays constant for all of the points at any moment of time. K plus U equals K plus U. If there is friction, then you can say K plus U equals K plus U, and for friction, I'll tell you what to do later. For elastic potential energy, remember 1/2 kx squared, we consider an average value between the minimum 0 and the maximum kx squared. You have 1/2 as the average. So elastic potential energy, 1/2 kx squared for the elastic force questions. There is your gymnastics competition with that pole bending. So you have some elastic potential energy in the pole, and the person will gain kinetic energy because there is elastic potential energy in the system of the person with the pole. So the faster that person runs and the more the pole bends, the more overall energy is stored, and you can transform that into gravitational potential energy to overcome the obstacle, to gain certain altitude. And this is the physics behind this high jump with the pole. And once again, K plus U equals K plus U, unless there is friction. And if there is no friction, it's just the same K plus U over and over again. So yeah, we do have electric energy, nuclear energy, chemical energy, all sorts of energies. And every time there is a transfer of energy to or from a system, there is work done by certain forces. And once again, good news, the overall principle of conservation of energy says that no matter what you do, you can't get energy out of the blue for no reason, and you can't lose energy for no reason. There's got to be some kind of a transfer of energy if you have a change in overall energy value. With no energy transfer to or from the system, energy is conserved. So the easy case was no friction. The hard case is with friction. So what if there is friction? Well, it means that a little bit of mechanical energy would be transformed into thermal energy. And if you rub your hands like very fast, you will feel the increase in temperature between the surface of your hands. And this is exactly the same process on how friction steals your mechanical energy and converts it into thermal energy. So you can't say K plus U equals K plus U anymore. It's not conserved. But the overall amount of energy is still conserved. And you might say K plus U before the interaction and K plus U after will be balanced if you will add the work done by friction force. And the biggest confusion here is that friction is usually opposite in its direction to displacement. Remember, displacement is in one way, velocity is in the same way, but friction would be opposite. And when you calculate the angle between the two vectors, you get 180 degrees. And cosine of 180 is -1. So work done by friction is always negative. And that's one of the confusions, and you really can't use this equation as it says because work done by friction is negative. So you want to add this work, but it's a negative value, which is confusing. So what I recommend you do at all times when you have friction is you forget the energy balance. Do not do energy balance, but rather do the change in kinetic energy equals work done by all the forces theorem or the principle. Because change in kinetic energy is a straightforward thing. Change is final, take away initial. So it's kinetic final, take away kinetic initial, that's your left side. And the right side is work done. And you can easily calculate work done by tension, gravity, normal, friction. And yes, work done by friction would be negative. That's fine. You don't care. You just add them up. And if you're adding up the negative, you're essentially subtracting, and that's exactly what you're going to get for the right answer. So if you want to make less mistakes with negative signs, then ignore the energy balance. That's called energy balance. And do the change in kinetic energy work done theorem. For friction, that's definitely what you're going to do. And we're going to practice, of course. I'll show you how it's done. And you choose the way it makes more sense for you. So net work done, including work done by friction. This is your right side, and change in kinetic energy is the left side. And change is final takeaway inertia. One last concept is the power. Power is just how fast the energy is transferred to or from a system. So it's a rate of change for energy transfer with respect to time. Or you might say how fast the work is done on the system or by the system with respect to time. So if you want some time constraints and compare the work done in 5 seconds or work done in 10 seconds versus something else, then you want to talk about power rather than just energy or work done. Units of power are watts, capital W, and work is joules, or energy transfer is in joules, time is in seconds, so it's joules per second. So watts are joules per second. No horsepower, please. If you see HP, horsepower, do not do horsepower calculations. You have to transform into watts. And I'll show you the conversion factor later. Yeah, you can think about power as the difference between walking and running, because walk or run, you're still going to burn the same amount of calories. You're still going to produce this much work done by your body. But if you walk, it's going to take more time. And if you run, it's going to take less time. So power-wise, it's different. But work done-wise, it's the same value. Okay, that's the end of lecture. Let's stop the recording and then do the classroom discussion.